Hello everyone. Welcome all of you to Physics for All by Shilpy Bhullar. As we have already discussed the physical significance of most probable speed, average speed and root mean square speed, so in this particular video, we are going to derive the expression for average speed. Let's get started. As you know, we are talking of gas molecules and whether they are in container or otherwise, they just keep on moving randomly. Average speed is defined as the average of the speed of all the gas molecules between V and V plus dV. So all the molecules that will be moving, they would be moving at different velocities. Some would be moving at particular velocity V, some would be moving at some velocity V plus dV. So we cannot guarantee that all the molecules would be moving with same velocity. This just doesn't happen. So we just pick a range that, okay, all the gas molecules which have speed between V and V plus dV. So this is the range that we have picked. And now whatever is the speed, we'll count all the molecules having speed between this range and then we'll take the average. How do we take average? Simple. In normal sense, how do we take average or mean? We first sum all the numbers and then we divide it by the count of the numbers. Same here, we are going to add up all the speeds of the molecules between this particular range V and V plus dV, and then we will divide it by the number of gas molecules. We have this range V and V plus dV, and now we consider that at any instant N1, N2, N3 and so on up to Ni molecules, they possess the speeds V1, V2, V3 and so on up to Vi. So there are N1 molecules which have speed V1, there are N2 molecules which have speed V2, N3, this is the count. N3 means the number. This could be any number. So N3 is the number of molecules which possess speed V3 and so on. Ni is again number of particles which possess speed Vi. And the speeds that we have considered here, V1, V2, V3 and so on up to Vi, they lie within this range V and V plus dV. Thus, if we have to find the average speed, how do we define its formula or the expression? So expression would be V subscript average, F, and that is equal to summation of NiVi upon summation of Ni. In the numerator, we cannot only mention Vi, summation of Vi. Most of the people think that if we are going to find average of velocity, all we have to do is just add up all the velocities. Most of you would be thinking that if this is the case, then we shall find the average speed as summation of Vi upon summation of Ni. But no, this is wrong. Why is it wrong? This would be the case if all the molecules, if we have that all the molecules, they would be having this Vi speed. Most of the time, this is the thing that we do often. We have summation V upon summation N if N particles are there and they possess the speed V. This is the scenario that we use in that particular case. If we have N number of molecules and they all possess speed V, then this is correct. But here this is not the case. We have different number of molecules and they are possessing different speeds. So simply summation Vi is again meaningless. So we have to tell. Now here this summation is actually, here this I is going from 1 to I, you can say, because here we have taken Ni molecules. One time we would put 1, that would mean N1 V1. Then we would have plus N2 V2 plus N3 V3 and so on. This would become N1 V1 plus N2V2 plus N3V3 and so on, NiVi. And this is what we have assumed because N1 particles possess V1 speed, not any other speed. Then N2 particles possess V2 speed, not any other speed. And the same goes for all the molecules. And this is the reason that putting Ni here is really important. Okay, so keep this in mind when we have different number of molecules and all the molecules are not acting alike. Specifically, when all the molecules are not behaving in the similar manner, then we have to consider the number of molecule as well. The same goes with energy. Sometimes we write down that N1 particles have U1 energy, N2 particles have U2 energy, and so on. In that case also, whenever we deal with any kinetic energy or other expressions, we write down in the numerator summation NiUi. So N is multiplied. That's the reason we have multiplied Ni with Vi in the numerator, and in the denominator we have simply summation Ni. This is just the way we find average. How do we find average? We sum up all the velocities or speeds and then we divide by the total number of molecules, and this summation Ni denotes it is total number of molecules. I hope this is all clear to you, this expression, why we have written it this way. Now let's continue with the derivation. As we know that number of molecules is going to be really large. Suppose you are standing in a room and someone asks you to count the number of air molecules present in that room. Is it possible for you to do that? Is it possible to actually calculate the number of molecules? We already know in a particular unit volume, the number of molecules or atom present is given by Avogadro's number. What is that? It is 6 into 10 raised by 23. In a cube, you can consider it unit volume if there. So this is the number and it is such a great number, we cannot count it. So counting molecules, atoms is just not possible. And this summation actually goes for counting purposes, something which we can actually count. But in case of molecules, this is not possible. And then what is the solution for that? We use integration. And that's why we have written here that assuming a continuous distribution of speeds, because they are just spread everywhere. And so we just consider continuous distribution rather than discrete distribution. Discrete is something like here in the picture, what you are seeing is discrete one, because this is how we actually represent things. It's easier to understand. But in reality, there's nothing like that. You will actually see cloud of molecules, and it's very difficult to actually count all of them. And whenever we deal with atoms or molecule or such microscopic particles, it's not possible to count them, and we never consider their discrete behavior. We always look for continuous behavior, continuous distribution, and that's why we are going to replace this summation by integration. Yes, we have a very good alternative for summation. Whenever we deal with stuff like this, we just simply switch to integration. And now let's write down the expression. It's VAV is equal to, now since the counting was from 1 to I, but here now we know that the number of molecules is going to be really large, and it's really large actually, and that largest number is infinity for us. So the limit is going to be 0 to infinity. Either no molecule is present, or if there are molecules, then they would be countless. And now, since in this case either we can have no molecule or very large number, and that large number is infinity, Now, what do we have to mention? See, if infinity is there, we have to represent that particular variable with respect to which integration would take place. For this v, just write down this v, and then we have nv dv. Because here we have NIVI, we have to consider the velocity also, the speed, the value of speed, as well as the number of molecules which are having that particular speed. So here this NV, subscript V, means the number of molecules which are possessing speed V. And V is actually the value of that speed. But we have to integrate it over V, over the speed itself. Because number of molecules which are having a particular speed, it's fixed. But what we are considering here is that speed is changing. See, now again, we have considered a range. We are talking of all the gas molecules which have the speed between this range, V and V plus dV. And thus we know that it is the velocity, it is the speed which is actually changing. Because often we use V for velocity, the symbol, that's why I keep on saying velocity, but just keep in mind that here we are just talking of speed in general. We are concerned with the magnitude, not the direction, because gas molecules, they just go in all directions, they just move randomly. Okay, the main point here to notice is that with respect to which we have to integrate, and here we have to integrate with respect to V, because we have considered a range of V. We have not considered any range of number of molecules, have we? No, we haven't. We are only saying that we have considered only those molecules which have speed lying between V and V plus dV. That's why it is the quantity which is actually changing or varying, and that's why we will integrate it over V. And in the denominator, it's going to be again 0 to infinity NV dV. Here we are not concerned with the speed, because in the denominator it's always the number of molecules, but again those number of molecules are not same. There are different categories. So we have different categories of molecules, we have different number of molecules which possess different speeds, and that's why again this expression would also be integrated over V. Now what we can write is, here this is going to be same, this is V and this is NV dV, but now in the denominator we can simply write down N, because ultimately this is the total number of molecules. We know that in a particular container or in a particular volume, we know what would be the count of molecules. But counting each of them one by one is difficult, but in general we can know the quantity. I hope you can understand this difference. In general, we can know the quantity, that how much molecules would be there. But if you go on counting each of them one by one, then that is impossible. This is the reason why we switch to integration instead of summation. This step we have written only because here in this particular step we were having summation Ni. So we have to show that instead of summation, now we are using integration. And only for this, only to represent this particular thing, we have written 0 to infinity NV dV here. But we know that this is nothing but total number of molecules. In fact, what we can do is that here we can mention NIVI upon N. We can do this here also, where N is total number of molecules. Now what do we get? This is the average speed, and that is 1 by N, because N is simply a number. We can bring it outside, and then we are left with the integration. V is again a number. Now let's see instead of this NV, what we are going to write down. So for this NV, we would write under root 2 pi n m upon pi kt raised to the power 3 by 2, then v square, then e raised to power minus mv square upon 2 kt. This is dv. Now what is this expression? This is the Maxwell-Boltzmann distribution law. The number of molecules, the expression for number of molecules given by Maxwell-Boltzmann distribution. So this is the expression. So directly for this NV, we have substituted this expression because ultimately we are talking of molecules and Maxwell-Boltzmann distribution law is specifically designed for molecules. Always remember, Maxwell-Boltzmann distribution law is for molecules. And here we are talking of molecules, and that's why we know the expression for NV, and the same expression we are going to write down here. Now we have to solve it. Let's see what else we can do. Now you can see here this is N and this is N, and again a number. So these two will get cancelled. So they just get cancelled. And then we can write 0 to infinity. This v will get multiplied with this v square. We have root 2 pi m upon pi kt raised to the power 3 by 2, and now v cube, right, because this v has got multiplied with this v square. So let's keep them in bracket. Then we have this v cube e raised to power minus mv square upon 2 kt dv. As the integration is with respect to dv, okay, v. So now we have clubbed the constant terms which do not involve v. Here you can see root 2 pi m, then pi kt. They are just constant quantities. So we have just grouped them, and now we are left with v cube e raised to power minus mv square upon 2 kt because these involve v and we have to integrate with respect to v. Now solving this is pretty hard. That's why we are going to use some standard integral. There are some standard integrals available which provide us predefined values. They just simply provide us the values and we need not to solve it because this really seems to be a complex integration. Let's see which integral would be of use. This is the standard integral which says if you have x cube e raised to power minus a, could be some number, x squared, and integration is with respect to x, then the answer is simply 1 upon 2a square. Now we can relate it. This x cube is basically here v cube. Then we have e raised to power minus, so yes, we have minus here, x square, here we have this v square, this particular term, and this whatever a. So a is what? A is m upon 2 kt. We can see this a is this particular quantity. Rest of the stuff is same. So the answer is going to be 1 upon 2a square. So we have to write 1 upon 2 and then we have to square this value of a, which is m upon 2 kt. So see how easy it is now to solve. Let's do that. Remember, we have this term already with us, which is a constant quantity because it doesn't involve v. So we have to write this first. So root 2 pi m upon pi kt raised to the power 3 by 2. Okay, and now we have to mention the solved value of this integral, because ultimately the integration would be with respect to this, and the range is 0 to infinity, and we have obtained the value. So it is 1 upon 2a square. Now we know what is our a. Let me mention here. Alright, so this is our a, m upon 2 kt. So let's write down here. Here we will be just, let me put the multiplication sign, and then this is 1 upon 2 into a square. So a is m upon 2 kt whole square. You can further solve it. This is root 2 pi m upon pi kt raised to the power 3 by 2, and then we have, because these terms are in denominator, and this will give us 2 2s are 4, and here we have 2 again. You can see here we have 2, and on squaring we would get m square upon 4 kt. So that 2 will get cancelled with 4, and we would be left with 2 kt upon m whole square, which is 8 kt upon m pi under root. You can see here how can we write this thing? This is 2 into 2 into 2. So this is the thing, right? And here we have this 2 and root 2. So very cleverly we have mentioned, because we want to bring all the terms within square root. So that's why we have written root 8 here. This is just the way of representation. You can use either way, okay? You can write it otherwise also. You can write 2 root 2 and the expression as well. No big deal about that. This is just a way of representing it. Let me write here down once again. We can write this 2 root 2 under root kt upon m pi. This is also allowed. Moreover, you can see here we have pi, and here we have pi raised to power 3 by 2. So if this pi goes in the numerator, we would be having pi raised to the power 1 minus 3 by 2. Just let me mention that. And then for m, again here we have m square, and this m raised to power 3 by 2. So that too would give us under root m. Okay. So these are the expressions. We have 2 root 2 pi 1 minus 3 by 2. Then m raised to power 3 by 2 minus 2, because 3 by 2 is in numerator, and then here we have m square in the denominator. Then for k, we have this k square in the numerator and k raised to power 3 by 2 in denominator. For t, temperature, we have t square in the numerator and t raised to power 3 by 2 in the denominator. So on solving, we get 2 under root 2 pi raised to power minus 1 by 2, m raised to power minus 1 by 2, k raised to power 1 by 2, and t raised to power 1 by 2. And what is 1 by 2? That is square root. So that's why we have mentioned here 2 root 2 under root kt upon m pi, because here pi and m, they have the power minus 1 by 2. And this 2 root 2 can also be written as root k. Further, on solving, we get that the value of 2 root 2 or root 8 is 1.59. This, the final expression, becomes 1.59, because this is the number. We know the value of root 2, 1.414. That multiplied by 2 would give us 1.59, and we have also used pi. So on dividing by pi, we actually get the value 1.59, and that's why here we have kt upon m left. This is the final expression. So 2 root 2 divided by pi, we are going to use the value of root 2. Then we are going to use the value of pi, which is 3.14. So on solving, because these all are numerical quantities, so we will get some number, and 1.59 is the number obtained. And K, T, M, these are just the value. K is Boltzmann constant, T is the temperature, M is the mass. So even we can substitute the value of K also, because it's a constant, we know its value, but still we just keep it inside the square root and as such, because while solving for different molecules we put its value. Temperature, again, at what particular temperature the molecules are, that would be there. And then which molecules are we talking of? So whether they are oxygen molecules or water molecules or any other molecules are there, so that the mass of those molecules would be put here, and then we would be able to find the average speed. See how easy it is. We need not to know the actual speed of the molecules. Just to find the average speed of a particular set of molecules, all we have to do is multiply 1.59 with square root of K, which is Boltzmann constant, T, at which temperature we have kept the molecules, and M, the mass of the molecule. See how easy it is. So this is all about average speed. We have obtained its derivation. Thank you.